In this lecture, we're going over buffers. Buffers are solutions which are homogeneous mixtures. But for you to have a buffer, you're mixing two things. If you want to have an acidic buffer solution, you're going to have a mixture of a weak acid and an ionic compound that is soluble that contains the same negative ion as your weak acid. So you have your weak acid plus a salt, which is your ionic compound, soluble, that contains a cation that is not going to make any difference in your buffer solution, but that negative part in your ionic compound will be the same negative part as the negative part of your weak acid, which means that what you have is a mixture of your weak acid and the conjugate base of your weak acid. If you have a buffer solution that is basic, now what you have again, it's a mixture, but what you're mixing is different. You will have a weak base, and in addition to your weak base, in that solution, you will have a compound that is a salt that contains the same conjugate acid as you will get with the dissociation of your weak base in solution. It will be easier if you actually see it with an example. For example, for an acidic buffer, you need your weak acid. HF is a weak acid. So you can see in HF, the negative part of your acid is the fluoride ion. So your weak acid by itself is not a buffer solution. Your weak acid by itself, it's your weak acid. Now, if to that solution where you have your weak acid, you add something like KF, potassium fluoride. Now you can see that you're mixing your weak acid with a compound that has the same conjugate base that you're getting from the dissociation of your acid. When HF dissociates in solution, you're getting H plus and F minus. So when you're adding KF to that solution, what you're doing, it's increasing the concentration of that F minus, which is the conjugate base that you're getting from your acid. So I have another examples here, acetic acid, where you have your acetate ion, and then you have sodium acetate with the acetate ion too. So you have a weak acid, and then you have an ionic compound containing the same conjugate base as your weak acid. And then we have a basic one right here, ammonia, and then you have ammonium chloride. So you have ammonia, which is your weak base, and then NH4 plus is the conjugate acid of your weak base. So when NH3 dissociates in water, the water will transfer the proton to the base, and you get NH4 plus 1. So this is the conjugate acid of NH3. So for you to have a buffer solution, you need to mix your weak base, ammonia, with any compound containing the ion of ammonium, NH4 plus 1. So you don't need, like what we're looking at, anything here, the positive ion, or here the negative ion. It doesn't matter which ion you have. What matters is the other part in your compound. For your acidic buffer, what it matters is the negative ion, which has to be the same negative ion that you have as part of your weak acid. And then for your basic buffers, then you're looking at the positive part in your compound, because that will give you the conjugate acid of the base. Now buffers are very useful. And they are very useful because they help to keep a pH of a solution constant. Not forever, but if you have a buffer solution, you can add small amounts of acids and the pH won't go lower. Or you can add small amounts of base and the pH of your solution is not going to increase. So you can watch this link here. It's a video going over buffers, basically the same things that I'm doing, but they have some demonstrations of how actually buffers work. Now, there are several properties of buffer solutions. So the first one, of course, is that they can resist pH changes. Okay? So a buffer solution will help to maintain a pH approximately constant or with minor changes. Your buffer solutions, depending on which type you have, if it's a basic buffer or acidic buffer, depending on which type you have. If you have an acidic buffer, you have a weak acid and a conjugate base. So you need to have significant amounts of each one for your buffer to actually be able to avoid changes in the pH. And then if you have a weak base or a basic buffer, your weak base and the conjugate acid, you need to have significant amounts of those two. And this is something that I will show you later. When you're adding a base to an acidic buffer, the base that you're adding to your buffer solution is going to react with the acid. Remember, in your buffer solution, you have the weak acid and the conjugate base of your weak acid. When you're adding a base to your buffer solution, the base reacts with the acid, forming more of the conjugate base, because you're neutralizing the base that you're adding with the acid that you have in your buffer solution. In the same buffer solution, if instead of adding a base now, you're adding an acid, the acid that you're adding is going to react with the conjugate base. Remember, you have both in your buffer solution. So if you're adding an acid to a buffer solution, that acid that you're adding is going to react with the conjugate base. And since you have a buffer where you have a weak acid, that's an equilibrium system. So let me show you something here. I'm showing you here a generic equation for a weak acid. So you have your weak acid, which is HA. And now, if you want to prepare a buffer containing that weak acid, you need to add any compound that contains a minus, which is the conjugate base of your weak acid. If you add a solution of sodium hydroxide, let's add a base to this mixture here. The sodium hydroxide, NaOH, is going to react with the acid to take the proton and form water. If you add to this buffer solution here an acid, let's say hydrochloric acid, HCl, your hydrochloric acid is going to react with the conjugate base. So it's been neutralized by the conjugate base. If your acid is combined with the conjugate base, your equilibrium is going to be shifted in that direction because you're decreasing the concentration of the conjugate base on the product side. If you're adding the base, you're removing something from the reactant side, which means that the equilibrium will be shifted towards your product. So that's how a buffer is actually working when you're adding an acid or a base to a buffer solution. Another thing that you need to be able to recognize is which substances you can mix to actually prepare a buffer solution. The definition is a weak acid plus its conjugate base, or a weak base plus its conjugate acid. You cannot prepare a buffer solution with strong acids or strong bases. When you have strong acids and strong bases, you have complete dissociation. There's no equilibrium present, which means that your equilibrium is not going to be shifted in either direction because you actually don't have an equilibrium. All of your strong acids, strong bases, which are strong electrolytes, will give you only ions in solution. So when you're preparing a buffer solution, that's one thing that you have to keep in mind. You need a weak electrolyte. So if you're looking at my two options here, A and B, in which solution do you have a buffer, or with which compounds can you actually prepare a buffer? In letter A, I have nitric acid and sodium nitrate. Now, two things for you to have a buffer: a weak acid with a compound that contains the same conjugate base or negative part as your weak acid. That part here is true. You have the nitrate ion and you have the nitrate ion. That is true. You have the same negative part in your weak acid and in the compound that you're mixing with it. But the other part is that you need to have a weak electrolyte, and nitric acid is a strong acid. So between your nitric acid and sodium nitrate, you cannot create a buffer using those two, because your nitric acid is going to dissociate entirely. You're not going to have an equilibrium. Let's check what you have in letter B. In letter B, that's the negative part of your acid, which is the same negative part in your ionic compound right here. So that part is true. Nitrous acid, this one here, it's a weak acid, which means that you have the two criteria that you need for you to actually prepare a buffer solution: a weak electrolyte with this one, it's a weak acid with a compound containing the conjugate base of your weak acid. So letter B should be the answer for that one. The calculation of the pH of a buffer solution. There are different ways of solving for the pH if you have a buffer solution. One of them is just using the ice table. It's an equilibrium system. When you have a buffer solution, you have the dissociation of your weak acid with an initial concentration for the conjugate base on the product side, which is the same type of problems that we did when you have a common ion. So it's the same thing. So we can actually calculate the pH of a buffer solution preparing the ice table. If it's a weak acid with a equilibrium constant value of 10 to the minus 4 or smaller than that, you can use the ice table, and then you can also use the assumption that your concentration, your initial concentration for the acid will change by a small number, and we can just assume that that small number is not going to change the initial concentration. In that way, you can get the pH of a buffer solution. But we have an equation that we can use also to find out the pH of a buffer solution, and it's the Henderson-Hasselbalch equation, or HH equation, like I'm going to label it from now on. So this equation, I have a version for your acidic buffers and another one for basics. So you have a pH equal to pKa plus the log of, you have two concentrations, the conjugate base and the concentration of your acid. This is similar to what you have in an equilibrium constant, concentration of your products over concentration of the reactants. When you have a weak acid that dissociates to give you the conjugate base, your conjugate base is the products. That's why you have conjugate base on the top part right there. And the acid is what you have on the reactant side, so that's why you have acid on the bottom part of your fraction there. For your basic buffers, you have POH because you will get hydroxide in solution, so that concentration is the one that you get, and we use this other equation. But you know that you can calculate pH for any basic solution using your relationship for pH plus pOH equal 14. So you have pKb plus the log of, and on top you have the conjugate acid, because that's what you have on the product side, over the base, which is what you have on the reactant side. When you have your basic buffer, you have your weak base dissociating to give you the conjugate acid on the product side. Just in case, because this is something that we have used before, P is just taking the log of a number. Remember, we have this equation pH equals minus log of the concentration of H plus in solution. So for Ka, which is your equilibrium constant for weak acids, Kb, which is the equilibrium constant for weak bases, we can do something similar. We can do minus log of the Ka, and that will give you the pKa value. Or we can do minus log of your Kb, and that will give you the pKb value. Some other equations I have listed there. Your pKa plus your pKb equals 14. This is something similar to pH plus pOH equals 14. Ka times Kb equals Kw, which is the equilibrium constant for your autoionization of water. 1 times 10 to the minus 14 at room temperature. So let's use the equations to calculate the pH for a buffer solution. First thing that you have to do to solve this type of problem is to find out which one is the acid, which one is the base, which one is the base, which one is the conjugate acid, all of those things. So going through the problem, I have calculate the pH, that's what you want. A buffer solution, so I already know that it's a buffer solution, and we use the Henderson-Hasselbalch equation. Now we have an initial concentration here, first concentration right there, 0.05 molar in benzoic acid. And then we have 0.15 molar in sodium benzoate, which is this one right here. Now, when you look at your equation, finding pH equals pKa plus the log of the conjugate base concentration of the conjugate base over the concentration of the acid. So we have two numbers. You need to identify which concentration corresponds to the conjugate base, which one corresponds to the acid. There are several things to do that. It's telling you benzoic acid. So that should tell you that that's the acid in your solution. So you have 0.05, that's the concentration of the acid. And then you have 0.150, which is the concentration of sodium benzoate. Benzoate is the negative ion that you have. And that's the conjugate base, that right there. Another thing, for benzoic acid, you're given a value of Ka. Ka is the equilibrium constant for a weak acid. You don't have a value of Ka for sodium benzoate because sodium benzoate is not a weak acid. You have a value of Ka for benzoic acid, that's your acid. Now you're given a value of Ka, which you can use to find the pKa. If you're using the ICE table, which will work perfectly fine to solve this problem here, if you're using the ICE table, you need the value of Ka to find how much is X, which is going to be the concentration of H3O plus, and you can use that to find out the value of pH. If you're using the Henderson-Hasselbalch equation, which is what we're doing here, then you're using the Ka value to find out the value of pKa because that's what you need in your equation. So to get your pKa value, you're doing minus log of 6.5 to the minus 5. And that will be 4.187. And that will be plus the log of concentration of the conjugate base, and that's 0.150, over the concentration of the acid, which is your benzoic acid, and that's 0.0. And I have 4.66. So the pH for this buffer solution that is prepared using your benzoic acid and sodium benzoate, with the concentration for the acid of 0.05, concentration for the conjugate base of 0.150, that pH is 4.66. Since you have the Ka value for your benzoic acid, you can actually calculate the pH just for benzoic acid in water. That's your ice table, and you have your benzoic acid dissociating to give you H3O plus the benzoate ion in solution. If you use your ice table to get the pH only for your benzoic acid, let me do that really quickly. That's going to give you 2.74. Just benzoic acid in water with a concentration, initial concentration of 0.050 molar, 2.74. Now, when you have the pH for your buffer solution, not just the benzoic acid, but the benzoic acid with the sodium benzoate together, look at the pH, 4.66. It's a higher pH, or less acidic. And it's less acidic because now you don't have only the acid dissociated in solution. When your acid by itself dissociates in solution, you're still getting some of that conjugate base, but it's a small amount. The Ka value 10 to the minus 5 is telling you that it's a small amount of the ions that you're getting in solution. Now, when you're actually mixing to your benzoic acid the sodium benzoate, now you're getting a higher amount of that benzoate ion, which is the conjugate base of your acid. The conjugate base will make the difference. That's why you have a different pH, higher, because you're getting more ions of that basic substance in solution. For the second problem here, you have NH3, NH4. You have a weak base with a conjugate acid. That's what you have in the second one. So in this one, we can calculate the pH by going through the equation of pOH. Look, you're given the value of your pKb. So we can do 4.75 plus. On the top part for this one, we need the conjugate acid. Ammonia NH3 is the weak base. Your ammonium chloride containing NH4 plus 1, which is the conjugate acid of NH3. That's the one that goes on the top part. And that will go over the concentration of the base, which is your 0.50. and that's giving you 4.35. Now remember that that number is not the pH. You're trying to calculate pH. Well, what you're getting is the pOH value. So to get the pH, you can do 14 minus 4.35. That will be 9.60. 9.65. Now you can do something similar to what I did or what I explained in the previous problem. You can calculate the pH, NH3, with that initial concentration using the ice table, NH3 plus H2O going through NH4 plus 1 plus hydroxide, and you calculate pOH, and then you do 14 minus pH to give you the pH value. If you do that for a solution of ammonia NH3 with a concentration of 0.5, the pH value will give you something close to 11.5. Now you can look at your two numbers. Only NH3 in solution, just NH3 in solution, 11.5. When you have your buffer solution here, 9.65, a lower value of pH. So from pure ammonia weak base to your buffer solution, that pH value is decreasing. Now that pH value is decreasing because the pH value for NH3, dissociation of NH3 in water, right? It's a basic number. You're getting your NH4 plus 1 plus your hydroxide ion in solution. The amount of NH4 plus 1, your ammonium ion, which is the conjugate acid, from the dissociation of ammonia in water, it's very small. So that's not going to play a big role in the pH of your solution. What is changing the pH in your solution is the production of your hydroxide from your ammonia getting the proton from the water. Now, when you have your buffer solution, you have a lot of your NH4 plus 1 coming from your ammonium chloride in this case. So a lot of that conjugate acid in solution is going to decrease the value of your pH because now you have that conjugate acid present in solution. Now, as I have told you before, it's not just the calculations what it's important, is what the numbers are actually telling you. You already know the relationship between the concentration of your hydronium ion and the pH, right? You know that part from the acids and bases part. So the higher the concentration of H3O plus or your hydronium ion in solution, right? It means that you have something more acidic. The more hydronium that you have in solution, the less hydroxide. Remember, your neutral solutions are 10 to the minus 7, 10 to the minus 7 for hydronium and hydroxide. That's how you get a neutral solution. For your acidic solutions, the concentration of hydronium is higher. For your basic solutions, the concentration of hydroxide is higher. Whichever is getting higher, like which one, if it's the hydronium getting higher, the hydroxide is getting lower. If your hydroxide is increasing, then the concentration of hydronium is decreasing. So when you have a solution with a high concentration of hydronium ions, it means that the concentration of hydroxide is low. So if you have a lot of hydronium, the pH value, it's an acidic pH. So you will have something lower than 7 or your pH below 7. Depending on the strength of your acid, you can have a pH value closer to 0 or a little bit between 2 or 3, depending on the strength of your acid. The Ka value, it's related to the concentration of your ions. Remember, your Ka value comes from the dissociation of your weak acid. The higher the dissociation of your weak acid, the more ions you have in solution, and the ions are what goes on the product part, which is the top part of your equilibrium constant expression. So the higher the concentration of hydronium ions in solution, the lower the pH, the higher the value of your equilibrium constant. The more ions you have in solution, the less molecules you will have. Remember, you're getting the ions from the dissociation of your molecules, the molecules of your acid. So the larger the number of molecules of acid that dissociates to give you ions in solution, the smaller the number of molecules that you will have present in that solution. And now the new part is the pKa. That's the new part here. So we can look at, I have here a list of weak acids with the Ka value. For them, you have 10 to the minus 4, minus 5, minus 7, minus 16. So the Ka value is decreasing in your list, which means that in that list of acids, the weakest one is the last one with 10 to the minus 16. The lower the Ka value, the lower the concentration of hydronium in solution, the higher the pH. So out of your acids listed here, all of them are weak, but the weakest one is the one with the smallest value for Ka. Now, the pKa, you know that it's minus log of the Ka. So you can calculate, I just calculated the first one and the last one. You can calculate these two here just to practice, and you can see all the numbers. But when you have your Ka value, the first one here, 6.5 times 10 to the minus 4, when you calculate your pKa, you get 3.19. When you do the same thing for the last one here, 10 to the minus 16, you're getting 15.7. So you can see that your Ka value is decreasing as you go down in that table. Ka is decreasing. And the pKa value is increasing. So the relationship between those two is inversely proportional. The smaller the value of Ka, the larger the value of pKa. The larger the value of your pKa, the smaller the value of the Ka. So I'm using here my relationship. Increasing concentration of hydronium means that the pH is decreasing, more acidic. It means that the value of your Ka will be larger because you have more ions in solution, which means that the larger the Ka value, the smaller the pKa. So you can look at the first one here, 10 to the minus 4, that's 3.19. 10 to the minus 16, this is the smallest Ka value, and you have the larger pKa, 15.7. So they are inversely proportional. Increasing the Ka means that the pKa will be decreasing, and the opposite is also true.